Okay, just some final thoughts before you take your test on fluid dynamics. We have some U-tubes and some springs and floating and all kinds of things for us to consider. What if we have a U-tube filled with a liquid? It could be mercury, water, whatever. And let's say we submerge an object that just barely fits in the tube, does not let the fluid come on the other side of it. And let's say we want to find out something about the density of that object. Well, again, we do have to start at the equal levels here. So this would be the barrier between the fluid and this object, and right here. We know that the height, we'll just call this H1, above the fluid here at this location is going to have some relationship with the height over here. And it's based on the idea that the pressure at this location here must equal the pressure of this location here. So let's say, let's call this rho 1, meaning the density of the fluid here, times G times H1 has to equal rho 2 times G times H2. And let's solve for a ratio. Let's solve for H1 over H2. That's going to equal the density of 2 divided by the density of 1. So, what are we looking at here? Well, it looks to me like H1 is greater than H2. So this number here is larger than 1. So what does that mean? Then the density of this object here must be greater than density than this object, than this fluid over here. And that kind of makes sense. It pushes more fluid that way. Let's take a look at here. Well, it looks to me like our barrier is about right here. Okay, and this, of course, would be H1. And this is going to be H2. And if we go over here, it looks like H1 is kind of small in comparison to H2. So this is going to be less than 1. So this tells us the density 2 of this object has to be less than the density of the fluid that it's in. Okay, so that's kind of how we look at it for those kind of U-tubes there. And remember, the pressure at the very bottom here is going to equal the density times G times the H all the way to here. And then you got to do the same thing, add that right there. So it'll be an additive effect. If I add an object to this side, the pressure on this side is going to go up. Okay, just a reminder of that. And likewise, we can calculate the pressure at the very bottom here. And that would just be density of our fluid multiplied by G times H from this spot all the way up to this level here, since there's only one thing that's there. So I just kind of want to remind you of that. Okay, what about if I have two fluids and maybe we have oil and water here, for instance? So let's just draw little lines on here to represent this fluid here, and this fluid here is all water. Okay, and of course, this fluid here would be oil. Let's just use like red lines to represent this. So one thing I didn't mention in the previous U-tube, of course, there is atmospheric pressure pushing down on both sides. So let's just call that P naught, and this way also is P naught. Now in our equation, you'll see that P naught cancels out. So again, I did not include it in the last question here. But again, we have to look at a barrier here. This is where the pressures must be equal to each other. And if we call this one, I'll change colors here. Let's call this one H1 from here to the top, and let's call this one H2 over here. Now again, we will have, and let's draw up the whole equation. So we'll have P naught plus density of oil, I suppose. So rho GH1 has to equal P naught plus rho GH2. In this case, rho would be the density of the water. Okay, and we do see that the P naughts do cross off. And P naught would be atmosphere on both sides since it's not moving on top of it. So what do we get again? We will get rho GH1 and rho 1 GH1 equals, rho 2 GH2. And we'll end up with the same equation that we had last time. So instead of a object placed in a U-tube, this is just oil. So we see that the equations work, very, very similar to each other. Now what about those springs? So what I've got is a spring with a mass attached to it. And there's two ways we can do a spring. We can, simply submerge the mass into the water, or we can have the spring kind of upside down in the water. And of course, we'll ignore any effect of this beam here and any effect of the spring. So make it kind of a simple situation here. So what are we dealing with here? Well, the gravity force, of course, is downward acting on this object. Okay, and we have force buoyancy going upwards. Okay, now assuming that we have not totally submerged this object, it can actually go down further. We'll still have force of the spring going upwards. Okay, so these are our forces that will be acting on the object. So we'll just say then, force net, okay, is equal to force of the spring plus force buoyancy minus force gravity. And in most cases, our force nets is going to equal 0, so let's place a 0 there. Okay, and this is a universal equation, so it works kind of for all things. So if we submerge this more and more and more, at some point, buoyancy and gravity will equal each other. The spring force will drop to 0. So when we have this object floating in the water, okay, our spring force will be 0, and these two will equal each other. Now, of course, if I somehow push this down even farther, and what's going to happen then is the mass is then going to try to force itself upwards, okay, because we push it in too far. It doesn't want to go down that far, so buoyancy in some cases might be larger than the gravity force, so it'll make the object come back up. Now what if we do a spring like this? So the object is floating, okay, and of course gravity is going downwards in this case, and we're going to assume that there's some tension force in the spring. So then we have the force of the spring here and force buoyancy upwards. We still have a similar net force equation. So force net is going to equal force buoyancy minus the force of the spring minus the force of gravity. Now, if by chance this object is just at the surface floating the way it wants to, and buoyancy might equal gravity, then your spring force in this case will equal 0. But if you submerge this even farther, you can actually cause the spring to stretch, and then you can actually increase your spring force here going against it. So it's possible to take this and drop it in further under the water and then actually start to stretch the spring, because the box is underwater and buoyancy is going to be greater than your force gravity, and therefore it's going to cause the spring to stretch. But in all cases, it will be at equilibrium, so force net indeed will equal 0. So hopefully this first video here makes good sense and will help you calculate well on our test. And I've got another video that's on the way.